In a variety of computer languages, the function Atan2 is the arctangent function with two arguments. The purpose of using two arguments instead of one is to gather information on the signs of the inputs in order to return the appropriate quadrant of the computed angle, which is not possible for the single-argument arctangent function. For any real number arguments x and y not both equal to 0, Atan2, y, x, is the angle in radians between the positive x-axis of a plane and the point given by the coordinates on it. The angle is positive for counterclockwise angles, and negative for clockwise angles. History and motivation. The Atan2 function was first introduced in computer programming languages, but now it is also common in other fields of science and engineering. It dates back at least as far as the Fortran programming language and is currently found in C's MathH standard library, the Java Math library, .NET System Math, the Python Math module, the Ruby Math module, and elsewhere. Many scripting languages, such as Perl, include the C-style Atan2 function. In mathematical terms, Atan2 computes the principal value of the argument function applied to the complex number x plus I. That is, Atan2, y, x, equals pr arg, x plus I, equals arg, x plus I. The argument can be changed by 2i without making any difference to the angle, but to define Atan2 uniquely one uses the principal value in the range of per mil currency I-euro. The Atan2 function is useful in many applications involving vectors in Euclidean space, such as finding the direction from one point to another. A principal use is in computer graphics rotations, for converting rotation matrix representations into Euler angles. In some computer programming languages, the order of the parameters is reversed or a different name is used for the function. On scientific calculators the function can often be calculated as the angle given when is converted from rectangular coordinates to polar coordinates. The one-argument arctangent function cannot distinguish between diametrically opposite directions. For example, the anti-clockwise angle from the x-axis to the vector, calculated in the usual way as arctan, 1/1, is I-4, or 45 a degree. However, the angle between the x-axis and the vector appears, by the same method, to be arctan, a 1 per a 1, again I-4, even though the answer clearly should be a 3 I-4, or a 135 a degree. The Atan2 function takes into account the signs of both vector components, and places the angle in the correct quadrant. Thus, Atan2, 1, 1, equals I-4 and Atan2, a 1, equals a 3 I-4. Additionally, the ordinary arctangent method breaks down when required to produce an angle of a plus or minus I-2. For example, an attempt to find the angle between the x-axis and the vector requires evaluation of arctan, 1/0, which fails on division by 0. In contrast, Atan2, 1, 0, gives the correct answer of I-2. When calculations are performed manually, the necessary quadrant corrections and exception handling can be done by inspection, but in computer programs it is extremely useful to have a single function that always gives an unambiguous correct result. Definition and computation. In terms of the standard arctan function, whose range is, it can be expressed as follows. Notes: this produces results in the range by adding 2 I-euro to negative results. Traditionally, Atan2, 0, 0, is undefined. The C function Atan2, and most other computer implementations, are designed to reduce the effort of transforming Cartesian to polar coordinates and so always define Atan2, 0, A0. On implementations without sign 0, or when given positive 0 arguments, it is normally defined as 0. It will always return a value in the range, I-euro, I-euro rather than raising an error or returning a nan. Systems supporting symbolic mathematics normally return an undefined value for Atan2, 0, 0, or otherwise signal that an abnormal condition has arisen. For systems implementing sign 0, infinities, or not a number, it is common to implement reasonable extensions which may extend the range of values produced to include a I-euro and a 0. These also may return none or raise an exception when given a nan argument. For systems implementing sign 0, Atan2, -0, x less than 0 returns the value AI euro Atan2, plus 0, x less than 0 still returns plus I euro. The free math library FDLIBM available from NITLab has source code showing how it implements Atan2, including handling the various IEEE exceptional values. For systems without a hardware multiplier, the function Atan2 can be implemented in a numerically reliable manner by the coordinate method. Thus implementations of Atan(y) will probably choose to compute Atan2(y) 1. The following expression derived from the tangent half-angle formula can also be used to define Atan2. This expression may be more suited for symbolic use than the definition above. However, it is unsuitable for floating-point computational use as it is undefined for y equals 0, x less than 0 and may overflow near these regions. The formula gives a nan or raises an error for Atan2, 0, 0, but this is not an issue since Atan2, 0, 0, is not defined. A variant of the last formula is sometimes used in high-precision computation. This avoids overflow but is always undefined when y equals 0. Variations and notation. In Common Lisp, where optional arguments exist, the Atan function allows one to optionally supply the x coordinate. In Mathematica, the form arctan, x, y, is used where the one-parameter form supplies the normal arctangent. Mathematica classifies arctan, 0, a0, as an indeterminate expression. In Microsoft Excel, OpenOffice.org Calc, LibreOffice Calc, and Google Spreadsheets, the Atan2 function has the two arguments reversed, Atan2, x, y, equals Atan, yx. In the Intel architecture assembler code, Atan2 is known as the FPATAN instruction. It can deal with infinities and results lie in the closed interval, I euro. For example, Atan2, x, equals plus I euro. Particularly, FPATAN is defined when both arguments are 0, Atan2, plus 0, equals plus 0, Atan2, plus 0, a 0, equals plus I euro, Atan2, a 0, plus 0, equals a 0, Atan2, a 0, equals AI euro. This definition is related to the concept of sign 0, that is, on most TI graphing calculators, the equivalent function is called RARPi and has the arguments reversed. On TI-85 the arg function is called angle, x, y, and although it appears to take two arguments, it really only has one complex argument which is denoted by a pair of numbers, x plus I equals. In mathematical writings other than source code, such as in books and articles, the notations arctan and tana1 have been utilized. These are uppercase variants of the regular arctan and tana1. This usage is consistent with the complex argument notation, such that Atan, y, x, equals arg, x plus I. On HP calculators, treat the coordinates as a complex number and then take the arg. Or CRARGATAN2STO, illustrations. The diagram alongside shows values of Atan2 at selected points on the unit circle. The values, in radians, are shown inside the circle. The diagram uses the standard mathematical convention that angles increase anti-clockwise, and 0 is to the right. Note that the order of arguments is reversed. The function Atan2, y, x, computes the angle corresponding to the point. The diagram below shows values of Atan2 for points on the unit circle. On the x-axis is the complexy angle of the points, starting from 0, and going anti-clockwise, through points, 0, 1, with complexy angle I euro/2, a 1, 0, with complexy angle I euro, 0, a 1, with complexy angle 3 I euro/2, to with complexy angle 0 equals. On this diagram one can clearly see the discontinuity of the Atan2 function. The diagrams below show 3D view of respectively Atan2, y, x, and arctan, yx, over a region of the plane. Note that for Atan2, rays emanating from the origin have constant values, but for Atan lines passing through the origin have constant values. For x greater than 0, the two diagrams give identical values. Derivative. As the function Atan2 is a function of two variables, it has two partial derivatives. At points where these derivatives exist, Atan2 is, except for a constant, equal to arctan, yx. Hence, 4. Informally representing the function Atan2 as the angle function yields the following formula for the total derivative. While the function Atan2 is discontinuous along the negative y-axis, reflecting the fact that angle cannot be continuously defined, this derivative is continuously defined except at the origin, reflecting the fact that infinitesimal changes in angle can be defined everywhere except the origin. Integrating this derivative along a path gives the total change in angle over the path, and integrating over a closed loop gives the winding number. In the language of differential geometry, this derivative is a one-form, and it is closed but not exact, and in fact it generates the first de Rham cohomology of the punctured plane. This is the most basic example of such a form, and it is fundamental in differential geometry. The partial derivatives of Atan2 do not contain trigonometric functions, making it particularly useful in many applications where trigonometric functions can be expensive to evaluate. References. External links: Java 1.6 SE Java doc, Atan2 at everything 2, pick basic pro solution Atan2 for a PIC18F, other implementations code for Atan2, bearing between 2 points, arctan and polar coordinates. What's arccos?